So let me go ahead and draft it out. I have a box of mass, let's go 2m, just like I did in third period, and a dart being fired at that box of mass m and velocity v. And let's say that this mass is hung on a cable length L. The dart's going to stick to the box, and in so doing, the box and the dart are going to swing upwards, making an angle of theta with the horizontal before coming to rest, and then beginning their motion back downwards. What I would like you to tell me is, what is theta in terms of the given variables in G? That's what I want you to tell me. So what is the maximum value of theta that we get in terms of L, M, V, and G? Now, this is not a problem that I feel like I should have to do. I think this is a problem I would like you to do. And in a few moments, I'm going to break you up into groups so you can kind of talk it out. But when you come back, I am definitely going to play Wheel of Participant List and pick on a couple of folks to kind of fire up their microphones and tell me what I should expect. Any question about what I'm asking you to find? All right, you know when I break you into your groups, the picture disappears. So you've got like 5 seconds to get that somewhere. 4, 3, 2, 1. Launch. All right. I look forward to seeing you in about, let's go with 3-4 minutes. But I'll first take a volunteer who maybe can give me one thing that they did in trying to solve this question. I'm willing to make it easy and let somebody volunteer for this. Otherwise, I'm going to play Wheel of Participants. All right. Wheel of Participants it is. And the mouse lands on, I'm looking over here, Jordan. Hey, Jordan, how you doing? Great. You're our first caller on Radio Shelton. Can you give me an idea of something you might have done here in trying to get the answer to this question? All right, so you have a couple of pieces that you definitely put in here. So you had theta equals what? L sine theta? All right, so I don't know how useful that's going to be, but I'll put it down anyways. And you had something about MV. Can you go back over that? Okay, let's start there. Would you agree, Jordan, that there is a collision that takes place in this problem? Okay, so what's the object that is moving before the collision? All right, so, and what's its momentum? That's it. So this is the momentum of the system just before the collision. What was not drawn, and this was purposeful, is recognition that there is this instantaneous moment in time where the dart has stuck into the block and the system now has some combined velocity after the collision, to which we don't know the speed directly. We do know that during this collision, momentum has to be conserved, and because momentum is conserved, we can probably figure out what that velocity is. I got some things going down in the chat. What's that? I am writing on the board. None of you can see it? So here we go. Okay, so now that you can see it, that probably makes a little bit of difference. So, of course, my screens are all a mess because I just got everything all over the place, and now I don't even know. Are you drawing? I think he is. No, nope, nice, not nice. Wow, you guys are vicious. The whiteboard is not updating. I substituted. Okay, are you drawing? Oh, there's a lot of stuff in there. Thank you, guys. Appreciate it. All right, back to work now, right? You can see this. You can see like maybe a happy face, things like that. Alrighty, so as I was saying, there's this instantaneous moment directly after the collision where our object is now basically transferred momentum. The dart transferred momentum to the dart block system. And it has to be equal to the momentum of the dart before, but now the system has mass 3m. So I'm probably anticipating that there's a final velocity that is lower than the original velocity by what looks like to be a factor of 3. And this represents the conservation of momentum. We know that momentum was conserved during this time because we have a Newton's third law interaction between the dart and the block. The dart touched the block touched the dart. Therefore, the momentum was conserved during that collision. We good so far? I guess so. Got like no feedback on that one. But we're gonna go forward. All right. Now this part's where the problem kind of takes a turn a bit. The dart block system has velocity vf, which we now know is equal to 1/3 v. But this system is being acted on by two other forces now. There's the tension in the string and there's gravity, both acting on the system in such a way that they are going to change the velocity of the system. However, gravity is a conservative force. So although gravity is part of the cause of this change in velocity, we know that during this time, the mechanical energy of the system is going to be conserved, even though momentum is not. Momentum is not being conserved because there's an external force acting on both objects. But energy is being conserved because that external force is gravity, and gravity is a conservative force. So at the bottom here, if we assume that this represents the lowest point that the problem attains, then we have nothing but kinetic energy down here at the bottom, right after the collision. And since there's going to be a clear change in height, I think we can state that that kinetic energy will be converted to potential energy in the block dart system. Now, this problem has, this correlation between how much momentum the system might have had and how much energy it has after the collision. But the connection between those two is precise. The momentum part that's conserved is just during the collision, just until the system has interacted through Newton's third law. The conservation of energy portion occurs right immediately after the collision, when the system has kinetic energy but begins to be slowed down by gravity and the tension. But the energy is still conserved, so we can state that the kinetic energy at the bottom, which is 1/2 times 3m times 1/3 v squared. Now we're looking at 1/2 mv squared here, and we're putting into each one of those buckets the things we know about each of our values. 1/2 mv squared. So m has to be the mass of the system. That's everything that's moving. And v is the velocity. I could put v final there, but v final can't be in my answer. So I put in 1/3 v, since 1/3 v can be. And this is going to be equal to, I would say mgh, but it's 3m gh. Now, here's where we're going to have to recognize that h can't be in our answer. We have to put something else in our answer. And this is something we've talked about, although there might be some relationship here. This is not the one we're looking at. And I might have heard Jordan wrong when she said that. What we really want to remember is that we have a relationship between h and theta for pendulums like this, where h equals L times 1 minus cosine theta. And this is a kind of a geometric relationship that we talked about first semester. One I would, again, encourage you to commit to memory. I have no way of knowing if it's going to be on the exam or not, but it's worth having at your disposal. And even a few people put it in the chat, or I see Vaughn did. It's good to have this at your disposal as a tool. Considering that, you can have your own set of notes, it seems clear to me they're going to know that you shouldn't be able to screw this one up. So I would start considering the things you might want to have on your crib sheet, and this should be one of them. I'm not going to do all the algebra here. I am going to do some, recognizing that the 3m's cancel. And there's an important implication I want to circle back to in a minute, but for right this moment, let's work towards an answer. This is going to be 118 v squared equals GL times 1 minus cosine theta. And I know some of you have already gone ahead of me and worked that out. And it's at this point I kind of want to stop for a minute. This is the portion that has theta in it. And although you could solve this for theta, sure. Let's just leave it as 1 minus cosine theta for just a minute. Not because I want to do anything, but I don't want to waste the time with algebra if I can avoid it, since we're already past the half point of the hour. If you look at this, it would suggest that the mass didn't have anything to do with the problem. And because it was canceled out. And that the only things that seemed to have something to do with the problem were the velocity, gravity, and the length of the string. That is not exactly true. What was the role that the mass played, and why is it disappearing here? Is there anybody who can venture a guess? You see it? It's my sad face. Not one of you? Are we even awake this morning? I mean, I got a whole list of super smart kids here. As I having to think about which one of these kids is the physics kid of the year, I'm wondering why I can't get one person to come down here and say why M isn't a part of this. Well, I feel my heart breaking. Or maybe the physics kid of the year doesn't appear in this list. Maybe that's what I'm sensing from this. All right. M does appear here. Maybe not the mass itself, but something about the mass does. The reason M canceled out isn't because the mass doesn't matter. It canceled out because I chose something from the very beginning of the problem that forced it to happen. I made the mass of the dart and the mass of the block proportional to each other. Because of that, we got this 1/3. That 1/3 is the part of the problem that deals with the mass. If the ratio of the masses had been different, that 1/3 would be different. But also, if I had instead had a capital M here, then I would probably get some ratio of the velocity in terms of both masses. Probably something like M over M plus M. Something to indicate that the ratio of the masses would still have something to do with the answer. By making the masses proportional, I make it easy on myself as a test writer to get an answer that's concise. But as a physicist, I want to be clear that gravity doesn't require the mass here, because kinetic energy and potential energy both have mass. But momentum does. The velocity after the collision is completely dependent on the ratio of these masses. And it's that part, the inertia during the collision, that determines how the masses play a role in the results of the collision. Now, I don't want to spend a lot of time here because this isn't the problem I want you to work on. You've done this problem before. This is first semester, old school stuff. You have to understand that where this problem goes is to start looking at combining things together. So instead of our dart striking a box, what if our dart instead strikes a rod of length L and mass 2m? This should be a clear similarity in what we've just done, but in this collision, the rod's moment of inertia is probably going to play a role in how this system behaves after the collision. Now, we only have a couple minutes left here, but what I would like you to consider, and I want you to think about it for a moment, because in this case, because I couldn't get a volunteer before, I'm going to ask for all 29 of you to throw me an answer here in the Zoom chat. Do you think replacing the box with the rod, do you think that will make the angle greater after the collision, or less, or the same? Meaning, if I replace the box with the rod, same mass, will that increase the angle, decrease the angle, or not affect the angle? I want to see your answer in the chat. Take a stab at it. You've got a 33% chance of being right. Well, at this point, I'm afraid we're going to see a big pile on because there seems to be a trend going. Once there's a trend, no one wants to be seen outside of that trend, that's for sure. Look at them go. So many of you who had your cameras on last week and no cameras this week. I'm sad. I don't get to see any faces. Bye. Hi, Caitlin and Sarah. That's cool. All right, that's a whole lot of increases. So apparently, either you understand that the rod's going to have a lower moment of inertia than the block had, and therefore will be easier to turn, or you may have worked it out already. I want to be very clear, though. We did our original problem using nothing but linear momentum and linear mechanics. But there's absolutely no reason we could not have considered that the moment of inertia of the original system was 2mL squared. It's a moment of inertia. It's a point mass. And it's a point mass with its mass concentrated a distance L away from the pivot point. So my fulcrum is right up there at the top. And it had a mass of 2m. So using my relationship for a point mass moment of inertia, I get 2mL squared. On the other hand, the moment of inertia of the rod, rotated about its center, is 1/3 times 2mL squared. So there's a big difference in the moment of inertia of the rod compared to the moment of inertia of the block. Now, here's what I would really like you to do. I would like you to come up with what 1 minus cosine theta is going to look like for this system. Take a few minutes, it should only take you 4 or 5, and do that. Now, for this one, you're going to have to use angular momentum for the collision. But while you're at it, consider redoing this question in terms of the angular momentum too. Our answer should be identical, meaning we should get the exact same answer whether we use angular momentum or not. So give them both a try. Now, I want to see your work tomorrow, but you don't have to submit it to EDSB. I'm just probably going to have, hit you up with some questions tomorrow when you come to class. And I have to hurry because they're going to yeet me right out of this meeting. And I won't have a chance to say goodbye to all of you. So I'm throwing down the gauntlet.
Good job, huh?
Yeah. That's good. It forces me to be